Alright, so here's a video about Kayles Formula and proofer codes. So this is like approximately page, more like 70 is where it starts. So this is about a question, and I'm going to start with like an ill-formed question. How many different trees are there with n vertices? And I put quotes around the word different, and I called this an ill-formed question because the first question I would ask about this question is, what do we mean by the word different? So here are two trees with three vertices, and sometimes when we draw graphs, we give names to the vertices and we write the name of the vertex right by the vertex. Sometimes we don't do this. And so here I have two trees. They are clearly isomorphic. And sometimes we have used isomorphisms to, roughly speaking, say that two graphs are basically the same graph. So in that sense, these two trees are basically the same graph, but if you pay attention to the names of the vertices, they're not really the same graph. For example, the vertex 3 has degree 1 here, and it has degree 2 here. So if we're going to talk about this question, we need to make it clear, what do we mean by different? Do we consider these trees different or not? And we could go either way on this. It depends what we want to do. If I'm considering these two graphs to be different, then I would say that I'm considering them as labeled trees. The word label refers to the names of the vertices, or the labels of the vertices. It's like I'm labeling the vertex by writing its name next to it. So these are not the same if we're considering them as labeled trees. However, if I took the labels off, meaning I just erased these names of the vertices, they would be the same. And so I would say if we're looking at them as unlabeled trees, then they're not different. They're the same. So here I started to make a chart to consider different values of n and how many unlabeled trees do we have, and then how many labeled trees do we have. So we're going to start with n equals 1. In this class, we don't consider graphs with 0 vertices. So we start with n equals 1. And there's clearly just one tree with one vertex. And in fact, there's only one graph at all with one vertex. It's this graph. And so there's one of them. Also, I mean, things are pretty trivial because we're starting with the smallest value of n here. Even if I consider it as a labeled graph, and let's keep in mind, when I talk about labels, I'm just going to use the labels 1 through n. I'm not going to use letters like A, B, C, or whatever. I'm going to be pretty uncreative with the labels. So the labels are all... the names of the vertices are just going to be 1 through n. And if there's just one vertex, you only have the one choice. You just put it has to be named vertex number 1, and so the graph can only really look like this, and so there's only one labeled tree. Okay, let's do n equals 2, and I have to warn you, things still aren't that interesting when n equals 2. How many unlabeled trees are there? Well, it can really only look this way. You have two vertices and they have to be connected by an edge. It has to look exactly like that, so there's only one possibility. Also, even if I put labels on them, I can call it 1 and 2. Like I have to use the names 1 and 2. And it has to look like this. Of course, you could ask, what if this one was number 2 and this is number 1? But I would consider that the same graph. The point is, whether I call this 1 or 2, which one's 1 and which one's 2. The point is I have two vertices, their names are vertex 1 and vertex 2, and they're connected by an edge. So if I were to flip this backwards, it would just be the same graph, just drawing it backwards. So there's still only one. All right. For n equals 3, things start to get a little interesting. Not for unlabeled trees. For unlabeled trees, you still just have the one possibility. The tree has to look like this. However, if you're looking at labeled trees, they are genuinely different. There are 3 genuinely different labeled trees with 3 vertices. And basically, it's just a question of which one's in the middle. 2 could be in the middle, and then 1 and 3 could be on the sides. And by the way, this is the same as if I went 3, 2, 1. Right? This would be the same graph if I switched the 1 and the 3. That would be the same graph. So I don't consider that as different. But for example, I do consider this one as different because now 3 is in the middle. And these are genuinely different, again, because, for example, the vertex 2 has degree 2 here, and the vertex 2 has degree 1 here. And then here's the third possibility where 1 is in the middle. So let's not go too far, but I do want to do n equals 4. For n equals 4, I could have, here's a possible tree. Here's another one. There are essentially only 2 unlabeled trees with 4 vertices. If you think about it, so one way of thinking about this is every tree has at least 1 leaf. So if I'm trying to make a tree with 4 vertices, what I can do is I can think of a tree with 3 vertices and think of how many ways can I add a leaf to that. So I'm looking at this picture and I'm thinking, what if I add a new vertex and connect it to one of these vertices, and how could it look? If I made a new vertex and connect it to the middle, then I'm going to get this kind of tree. If I make a new vertex and connect it to the end, then I'm going to get this kind of tree, right? And those are essentially the 2 possibilities. I could make a new vertex and attach it to the other end, but then I would also get this kind of tree. So I don't really get anything new that way. But so yeah, we have these 2 possibilities, and then how many labeled trees are there? And this is where it starts to get a little bit hard to count. Here's how I would suggest doing this. Let's imagine all the different ways I could put labels on these vertices. So it's like I took an unlabeled one and I'm imagining how many different ways I can put labels on it. This is a lot like the one we did before. All that really matters is what is this sort of central vertex, like the vertex that's adjacent to everything else. This could be vertex number 1, or it could be number 2, or it could be number 3, or it could be number 4. There's 4 different names that I could give this vertex. And then whatever name I give to this vertex, these other 3 are just the other ones. And it really doesn't matter which is which. The point is I have this vertex that's special and it's adjacent to all the other ones. So there are 4 ways to put labels on this tree. And again, the 4 different ways are that this vertex could be number 1, and these could be 2, 3, and 4, or this could be number 2, and these could be 1, 3, and 4, or this could be 3, and these would be the rest, or this could be 4, and these would be the rest. Okay, how many different ways could I assign labels to this tree? And like I said, this turns into kind of a slightly difficult. I mean, well, things haven't gotten truly difficult yet, but we're only doing n equals 4. And then they're starting to get slightly difficult. This is a difficult counting problem, potentially. But here's how I would attack this one. I'm going to give names to these vertices. It could be 1, 2, I mean, the possible names are 1, 2, 3, and 4. And I can basically consider every possibility. So it could be 1, 2, 3, 4, 4, 2, 3, 1, etc. However, some of those some of those are the same. For example, the labeling 1, 2, 3, 4 is essentially the same as if I went 4, 2, 3, 1, because that would be the same graph. It's just if I turn it upside down, then it's the same graph. So in other words, if I do the same sequence forwards and backwards, it's the same. So here's what I'm going to do. There would be 4 factorial ways to put labels on these. I have 4 choices for which label to put here, and then 3 choices for which label to put here, and then 2 choices, and then 1 choice, right? However, that counts everything twice as much as it should be counted, because every sequence appears, if I count it that way, that's counting every sequence backwards and forwards. But backwards is the same as forwards for this situation. 1, 2, 3, 4 is the same as 4, 2, 3, 1. And any particular sequence would be considered the same labeled tree as that same sequence backwards. So I counted everything twice as much as I meant to, or I counted everything twice when I meant to only count it once. So I'm going to take that and cut it in half. That's what I'm going to do. What do we get? 4 factorial is 24, so this is 12. So I got 4 plus 12 is 16. There are 16 labeled trees with 4 vertices. Okay. And I won't do n equals 5 for this. It's possible to do n equals 5 using the same type of reasoning, but it gets a bit tedious. Let me talk about Kayles formula. Kayles formula is basically a formula for this column. For general n, the number in this column is n to the n minus 2 power. For the first couple of values of n, it's a little bit weird, but it's true. Like n equals 1. 1 to the negative 1 power is 1, so the formula is right. What about when n equals 2? We get 2 to the 0 power, which is 1, so that's right. When n equals 3, we would get 3 to the 1 power, which is 3. And when n is 4, I would get 4 to the 2 power, which is 16. So that's what this formula is telling us. It's not a terribly difficult formula to guess if you're looking at this column of numbers, especially if I were to fill in, say, like what is the entry for n equals 5 and n equals 6. It's not hard to recognize like that these are powers of n. And so people noticed this pattern. It's not a terribly difficult pattern to guess. and people noticed it, but it was quite a while between when somebody noticed the pattern and when somebody really proved formally that it was true. And I believe the story is that, yeah, maybe the story is that Cayley noticed that the formula was true and then Proofer actually proved it. I could be wrong about that, though. But Proofer is the name of a person who provided a proof. I forget if it was the first proof or what, but it's a well-known proof. So let's talk about these things called proofer codes, and this is part of the proof. I'm not going to give a completely formal proof that Kayles formula is true, but I'm going to give you a hint, and it has to do with proofer codes. So here's what we're going to do. We're going to define a bijection. So this is going to be a function that is one-to-one and onto. And the domain of the function is going to be the set of labeled trees with vertices from 1 to n. In other words, it's precisely the objects that we're trying to count right now with Kayles formula. So that's the domain of the function, and the codomain is or no, sorry, yeah, well, it's the same. In this case, it's the same, but I'll call it the range. The range of this function is the set of sequences of length n minus 2. So it's a sequence of numbers. The length is n minus 2, and each term of the sequence is a number from 1 to n. So if you think about it, if we can show that there is such a bijection, then that proves Kayles formula. A bijection between two sets is proof that they have the same cardinality, right? Two sets have the same cardinality if and only if there's a bijection from one to the other. So if we have such a bijection, that means that the set of labeled trees that we're trying to count has the same cardinality as the set of sequences that we're discussing over here. But it's easy to see the cardinality of these sequences. This is just a sequence whose entries are from 1 to n, so basically each entry of the sequence has n choices, and the number of terms in the sequence is n minus 2. So, in other words, the number of such sequences, the cardinality of the range is, well, I have n choices for the first one and then n choices for the second one. So the number of such sequences would be just n times n minus 2 times. In other words, n to the n minus 2. So if we establish that there is a bijection between these two sets, that proves Kayles formula. Okay, so let's describe this bijection. And again, it's a bijection whose domain is the set of labeled trees on n vertices. So in this picture, I just drew one example of a labeled tree with 8 vertices. So I guess n is 8 in this picture. And of course, there's a lot of trees in this set. I just drew one of them. So there's a lot in this picture that I'm not drawing. And over here, I have the set of sequences, and since n is 8, this should be a sequence of length 6. Hopefully it is. Yeah, it's 6, and each entry is from 1 to 8. And what I'm telling you is that this particular tree goes to this particular sequence. And again, let me emphasize that this bubble, you have to use your imagination that there's a lot of other trees in this bubble. And likewise, there are a lot of other sequences in this bubble. You know, in this bubble, you have to imagine you have every possible sequence of length 6 whose entries can be from 1 through 8, and there's a lot of those. In fact, there's 8 to the 6th of those, and that's a huge number. But I'm telling you that this particular tree goes to this particular sequence. And let's talk about how that is, and this is my description of the function. It's not the easiest function to describe. And yeah. You can see a formal description in the book. I'm just going to describe it in sort of out loud on this video. But this algorithm is a description of what we're really doing. It's not that hard, though. Let me describe what we're doing. I'm going to take this tree. In order to describe this function, I have to describe a way of basically you give me the tree and I will give you the sequence. And I'm going to describe how you come up with the sequence given the tree. So I take whatever tree you give me. I'm going to look for the lowest labeled leaf. So that you gave me a tree, it definitely has some leaves. Every tree has at least 2 leaves. And by the way, we're assuming that n is at least 3, so this is not a trivial tree. So you give me a tree, it has some leaves. I look for which one has the lowest label. So, for example, in this one, I see a tree or a leaf whose label is 4, 3, I see 6, and 7. And 3 would be the lowest labeled leaf. What I'm going to do is I'm going to record the label of its neighbor. This is a leaf, right? So a leaf has just one neighbor. So I look at its neighbor and I record that label. I see that's a 2. That's why that's a 2. So I just described how to look at the tree that you're given and come up with the first number in your sequence. And then I'll explain how to come up with the rest. So what I drew down here is like a sequence of how this goes. And this is going to explain how to fill in the other numbers. So here's what we do. This down here is just a redrawing of this original tree. I just drew the same thing down here. And I circled 3 because it was the lowest labeled leaf. And so as I explained, the fact that 3 is a neighbor of 2 is the reason why that's a 2. So here's what comes next. I remove that leaf. I remove the lowest labeled leaf. So I redrew this picture, but now the vertex 3 that would have been here is now gone, along with the edge that touched 3. And now I just do it again. I look for the lowest labeled leaf in the new graph. So here's a 4, a 7, and a 6, and the lowest labeled leaf is a 4. Its neighbor is a 1. That's why that's a 1. So that's explaining the second term. Then I do it again. I remove the lowest labeled leaf. I redrew the graph here. This is the same thing as this, except the vertex 4 is gone. I look for the lowest labeled leaf again. And keep in mind that something that wasn't a leaf before can become a leaf. Like 1 was not a leaf before, but then after I remove the 4, 1 becomes a leaf. In fact, 1 is now the lowest labeled leaf, because of course it is. If 1's a leaf, then there's no labels that are less than 1, so that's got to be it. So 1's the lowest labeled leaf. The neighbor of 1 is 2. That's why that's a 2. Then I remove one, I go down here, I look for the lowest labeled leaf. The lowest labeled leaf is now number 2. Its neighbor is an 8. That's why that's an 8. Then I draw the new graph where I remove that lowest labeled leaf. I'm here. I see 2 leaves, 6 and 7. 6 is the lowest one. Its neighbor is 8. That's why that's an 8. I remove the 6. Now I'm here. There's 2 leaves, 7 and 8. 7 is the lower one. Its neighbor is 5. That's why that's a 5. And that brings me down to just 2 vertices, and then I just stop. Right, like when you get down to 2 vertices, you just stop. But yeah, so that's how you come up with the sequence if you're given the tree. Okay, so where does that put us? We've defined a function whose domain, and I wrote it more formally this way, the domain is the set of labeled trees whose vertices have the labels 1 through n. And the range is the set of sequences of length n minus 2 whose entries are all from 1 to n. And we defined a function. I gave you instructions for how to take something in the domain and calculate the thing in the range that it corresponds to. So that's a function, but I called it a bijection, and it's important that it's a bijection because we're trying to use this as an argument that 2 sets have the same size. I try not to use the word size this way. Cardinality. I want to show that this set has the same cardinality as this set. So how do we know that this function that we defined really is a bijection? A bijection is supposed to be a one-to-one and on-to function. It's another way of describing as a bijection as a function that has an inverse. And this is where I'm going to, so I'll admit that I'm not fully providing a formal proof of this part, but I'm going to describe the inverse. I'm not going to fully prove that this is a valid inverse function, but I will describe the inverse function, and it is the inverse function. I'm not lying to you. I'm just not going to prove it. So, how does this go? This is algorithm 3.22, if you want to look at it. Here's my description of it. My description looks slightly different, but it is the same algorithm. We're going to have a sequence that we call lowercase s, and keep in mind, I have a lowercase s and a capital S in order to make them look different. My capital S has these thingies on it. So this is lowercase s. I'm going to have my lowercase s sub 1, and that's going to be the sequence. Because, let me actually go a little bit slower here. To do an inverse function, basically the inverse should go from this set to this set. In other words, conceptually, the original function takes a labeled tree and calculates a sequence of numbers based on that labeled tree. The inverse should go the other way around. The inverse should take a sequence of numbers that you give me and tell me a labeled tree that is associated with that sequence of numbers. In particular, like the inverse should be able to tell me, for example, for this particular labeled tree and the particular sequence that it came out with, the inverse is basically a way of taking this sequence and telling you what tree it came from. So that's what the input for the inverse should be. It's the sequence of numbers, and then the output is going to be what tree did it come from. So I call that the sequence little s1. And I'm going to have a set, capital S1, that's just the set of all the labels 1 through n. And now I'm going to repeat the following. Let k sub I be the smallest element of the set capital S sub I that is not in the sequence little s sub I. I'm going to draw an edge from k sub I to a sub I. And then I'm going to remove k sub I from the set big S sub I sub 1, and the result is going to be big S sub I plus 1. Then I'm going to remove a sub I from the sequence little s sub I to make the sequence little s sub I plus 1. After doing this, there should be only 2 elements left in the set capital S sub n plus 1, and I will draw an edge between them. The resulting graph is supposed to be, and it is, the tree that is associated with the original sequence that we were given. In other words, T is F inverse of that sequence. So I went a bit fast describing the algorithm, but I'm going to illustrate it. And I'd like to, and again, this is the part that I'm not formally proving. I'm not formally proving that this is genuinely a function that always gives you a tree, for example. However, I will illustrate it. Right, so I'm going to illustrate and so right, what I'm going to do is I'm going to take the tree. Basically, I'm going to look at this correspondence again. In other words, this particular tree and this particular sequence. And like I was saying, this procedure that we just described is supposed to be the inverse of the original function that we described from the trees to the sequences. And I showed how to start with this tree and get this sequence according to the original procedure. And then I described a procedure that I'm claiming is the inverse function. In other words, if you give me this sequence, even if I don't know that it came from this tree, I should be able to figure that out. So let's talk about how to take this sequence and figure out which tree it comes from if we don't already know. And so I'm going to follow the algorithm that I described, which is in the book. It's algorithm 3.22. And actually, before I get into it, let me just describe how when we were going this direction, like starting with the tree and coming up with the sequence, this procedure involves starting with the tree and then removing a leaf and then removing a leaf and then removing a leaf. So as we do that, it's like we're deleting vertices and edges. And let's just pay attention to what we're about to do, which is rebuild this tree. So I drew the vertices 1 through 8, and I haven't drawn any edges yet. And we're going to draw edges there, and we're going to see that the tree that we end up drawing is the same tree that we started with to get that sequence. And in fact, the procedure we're about to follow is literally like doing this backwards, so to speak. Okay, so now I'll actually start. What do the directions say? The directions say that we're given a sequence little s1, and we have this set big S1 that's just from 1 to n. So we were given a sequence of length 6. That means that n is 8, because the length of the sequence is n minus 2, so n must be 8. So my set big S1 is just going to be the set of numbers from 1 through 8. And my sequence little s sub I is the sequence that I'm trying to do. It's this sequence, the one we're trying to figure out which tree it came from. So that's how I start. And then what do the directions say to do? The directions say to find the smallest element of the set big S that's not in the sequence little s. Okay, well, so 1 is in here, 2 is also in here. I'm looking for the smallest thing that isn't in here. 3 is the smallest thing that is not in here. So k sub I is 3. Whoops, k sub 1, because I is 1. A sub 1 is 2. That's just the first term of the sequence. And so I am going to draw the edge from k sub I to a sub I, because that's what the instructions say to do, to draw the edge from there to there. So I draw the edge from 3 to 2. And then I'm going to remove k sub I from capital S sub I. So this is telling me how to make S sub 2. So I'm going to remove this. 1, 2, 4, 5, 6, 7, 8. I also remove the first number from this. So 1, 2, 8, 8, 5. Okay, and then I'm about to repeat, but before I do that, let's just look at the edge that I drew so far. This edge was the first one that we removed when we were doing this the opposite way. When I started with a tree and I came up with this sequence, the very first edge that got removed was the edge from 3 to 2, because 3 was the lowest labeled leaf and its neighbor was 2. And so this got removed. And I just want you to notice that that's the first edge that we drew when we were carrying this out. And that's how this is going to work. Actually, look at the second edge that we removed. The second edge that we removed here was the edge from 4 to 1. And as we're about to see, that's the next edge that we're going to put back. Okay, so let's do it. I look for the smallest element here that does not appear here. So 1 does appear, 2 does appear. There's no more 3 here, so that doesn't appear here, but that doesn't matter because it has to be something that appears here that does not appear here. So 4. 4 is the smallest element that does not appear here. So that's what I call k sub 2. A sub 2 is just the next thing here. It's not hard to find a sub 2. And then I draw the edge from this to this. Like I said, that's the edge from 4 to 1. And I'm going to start going faster. Of course, the next thing I do is my new set just is the same as the old one. It just doesn't have 4 anymore. And my new sequence, I just basically knock off the 1. Okay, now 1 is the smallest thing here that does not appear here. So K sub 3 is 1. A sub 3 is just the first entry here. So I draw the edge from 1 to 2. My new set will not have a 1, so 2, 5, 6, 7, 8. This will be 8, 8, 5. Now 2 is the smallest. The smallest thing I see here that I do not see here. So 2 gets connected to 8. I knock this off. 5, 6, 7, 8. I knock this off, so 8, 5. Let's see. 5 does appear here, 6 does not, so 6 is the smallest. So that's my next K. I connect that to the first thing here, so 6 gets connected to 8. My next set is 5, 7, 8. My next sequence is just plain 5. I look for the smallest thing here that doesn't appear here. That would be 7. So my next K is 7. My next A is, of course, just the 5, so I draw an edge from 7 to 5. Now I'm down to a point where my set just has 2 elements and my sequence is empty. And so what did our instructions say to do at that point? After repeating this enough times, there will just be 2 elements in my set, and you just draw an edge between them and then you're done. So I have 2 elements, 5 and 8. I draw an edge between them, and I'm supposed to be done. And sure enough, this tree that we just drew is this tree. All the same connections are there. And yeah, so I'm not providing a formal proof that this really is the inverse. I just showed you an illustration that we were able to recover the original tree given the sequence and by following these instructions. But it does in fact always work. This function really is a bijection. And the proof of that is or was the original proof of Kayles' theorem. So yeah, that's Kayles' theorem. The number of labeled trees is n to the n minus 2 power.